Welcome to this module. In this module we will see the other applications of operational amplifier. Until now what we have seen? We have seen the characterization of op amp, like some characteristics of op amp, and then we have seen a few functions of the op amp, right. A function of an op amp like summing amplifier, a function of an op amp like differential amplifier, a function of an op amp that we saw yesterday or in the previous module, which was the instrumentation amplifier, correct. So, see it is good to understand different applications of op amp, right. It can be integrator, it can be differentiator, it can be filter, and as and when I told you that I will start from the basic and slowly show you the complex circuits. So, that is very important part, and we will see how we can make the complex circuits. So, let us see on the screen, the integrated circuits, MOSFET, op amps and the application, that is the title of our course, right. And today's experiment, in today's module we will see several application of the operational amplifier, which are comparators, differentiator, integrator and filters. So, we will discuss each of those examples in detail, and I have already taught you this thing in the theory classes, and we will see today how can we actually implement the op amps as comparator, and then we will follow for differentiator, integrator and filters. So, if we go to the first slide of this module, we want to use op amp based comparators. So, we should first understand, and we have already understood in the theory class, what is a comparator. Let us refresh. A comparator is a device that compares two input voltage and provides a digital output, either high or low signal based on the input signal. So, what does that mean? It will compare, right. So, it is very easy. If I give you two signals and if I ask you which signal is high, which signal is low, you can use the comparator and you can tell which one is high and which one is low. Suppose the signal A is high, that is, you see we are applying the signal to the comparator, but the way we use comparator is in different way. We apply a constant voltage which we call a reference voltage, and with respect to this reference voltage we apply another voltage and compare to this reference voltage. That means that suppose this V in, right, this is my analog input voltage and this is my reference voltage. This reference voltage is constant, and this will change whatever input signal is there. Suppose I have kept reference voltage as 3 volts, all right. Now, if my input voltage is 2 volts, then my output would be 0, all right, and or we can also say minus VCC, 0 or minus VCC, go to the negative saturation region. So, we can say 0 or minus VCC. Same way, if my input voltage, the input signal is 3.1 volts, then there is difference of 0.1 volt, right, 3.1 volts here, 3 volts here. So, there is a difference of 0.1 volt. This difference will cause the output to go to the positive saturation or positive plus 5 volts. So, if I apply plus 5 volts here, minus 5 volts here, compared to the signal, I will get the output. Here what we can see, let us see what we have written. This is, I have shown you an example, and it is a simple 1 bit analog to digital converter. Now, yesterday I told you, right, day before that, when we are looking at the modules, that what exactly A to D converters are there and what are the D to A converters. So, we have seen that when you apply analog voltage and you want to get the digital output, you have to use A to D converter. There are several types of A to D converters, several types of D to A converters, that we will we already had a glimpse of those, and the detail of those would be covered in a next course, which is a higher level than what we are learning in this particular course. So, we will see some advanced version of A to D, D to A, and some applications or in terms of projects of operation amplifier at several applications. Also not op amp, but also certain analog circuits, analog electronic modules, and we will take few examples, whether it is a ECG or whether we have to control a motor or we want to control the LED. So, we will have several examples in the next course, not this course. So, that you understand that okay, in this course you have learned about op amp, you have learned about the indicator circuit, you have learned about their applications, but what are the advanced versions, how now you can actually implement those circuits and formulate a project. Alright. So, that will be the part of another course, but let us focus on this one, which is the op amp based comparator. And once you know that the comparator is nothing but a device that compares two input voltages and provides the output, right, based on high or low signal based on the input signal. That means, if the input signal is higher than the reference voltage, it will give you a high, if the input signal is less than reference voltage, it will give you low, correct. Now, it has two analog input terminals and one binary digital output terminal. So, this is the output terminal, these are input terminals, input 1, this is input 2, right. So, these are two analog input signals or terminals to which we apply analog signal, alright, and here we get either plus or minus. That means that it works as a binary. Binary, what is binary? Binary has two, one is when it is high it is 1, when it is low it is 0, binary, right, only 2 digits, 1 and 0. So, most of the digital circuits that works on the binary signals, and few of the circuit works between 1 and 0, is 1 and 0, the intermediate state between 1 and 0, and that is what we call fuzzy logic. We call it a fuzzy, F-U-Z-Z-Y, right. So, understand what is fuzzy logic, why we are using it, whether it is important or not, but why I am telling you this thing, because you should not just assume that there are when you talk about digital is 1 and 0, there can be many intermediate state between 1 and 0 as well, alright. But for here when we talk about digital, we are only talking about two states, that is 1 and 0. We are not considering the fuzzy logic, we are not considering that. So, let us not consider fuzzy logic here, what we consider is just digital output, that is 1 which is high, 0 which is low, or plus VCC and minus VCC, alright. So, we have seen three things, right, we have seen three things. First is that op amp, let us see once again, as many times you repeat it is better, because our brain remembers many times when you give the same kind of information, right. If you have taken a course on artificial intelligence, you will see number of iterations that you have to give, and number of time you have to train your ANN to make it close to what we actually want to get the output. So, number of times you train your brain, number of times you say the same thing, your brain tries to remember it. So, that is why we are kind of repeating the same things, so that we all remember what exactly comparators are. So, let us see one by one. Again, a comparator is nothing but two input voltages providing a digital output either high or low based on input signal. First point. Second point, it is a 1 bit analog to digital converter. Third point, it has two analog input terminals and one digital output terminal. These three things we have seen, right. Let us see the fourth thing. Fourth thing is a comparator is operated in an open loop configuration, thus act as a specialized high gain differential amplifier. Open loop extremely high gain, we all know, right. Closed loop we can change the gain, open loop is we cannot change the gain, right, is extremely high. Now, it will also act as a differential amplifier, because it will take the difference between the two input voltages and it gives the output, but it is not really amplifying it, because there is no feedback here, we cannot have any amplification factor, right. But at the same time, why is amplifier? Because it will directly give you plus VCC. So, minus 0.1 volt, for example, let us say 2 volt is here, 1 volt is here, 2 minus 1 is 1 volt, right, at the input, but output directly we see high or low, which is not 1, it will be minus VCC plus VCC. So, it is extremely high, that is why we say kind of differential amplifier, even there is no feedback or there is no feedback resistor, and there is because it is open loop op amp, it is the where it has very high gain, alright. Now, what we see next, that they are commonly used in devices that measure digitized analog signal such as A to D converters and controlling applications. That is the application of the op-amp based comparator. So, once we understood that okay, this is a open loop gain, okay, open loop high gain, then we see that whatever the difference, right, our output will be either plus or it will be minus, it is digital 1 or 0, similar kind of things. Now, when you do this, that means that it is trying to convert the analog input into digital output, that means it can be used in A to D converters, alright. Finally, a typical op amp as comparator is shown in figure 1. You see figure 1a, this one, which is your figure. Now, what exactly this figure is, let us see. You can see here, if V in is greater, consider this first case, when V in is greater than V reference, then V out is plus VCC. When this voltage is higher than this voltage, then your V out gets VCC, alright. Second case, when V in is less than V reference, V out goes to minus VCC, right. So, if you see here, this particular line is when V in is greater than VCC. So, from here it goes to saturation, here it goes to my negative saturation region, this you can see V in less than reference, this V in greater than reference, and this is what is the normal region, normal linear region. This is the region, this is in, like if you draw like this, the shade here, let's see clearly. This region, this we call normal linear region, alright. This region is saturation, this is also saturation, alright. So, it is very easy to understand comparator. Now, every one of us knows that when you apply a voltage input signal which is greater than V reference, our output will be plus VCC. When our voltage is less than V reference, output would be minus VCC, alright, easy. So, now let us go to the next slide and let us see the example of the op amp based comparator. So, suppose you are given a circuit which is here, the circuit is given to you, alright, and you are asked that consider the op amp as comparator configuration as shown here. You can see the bias voltages plus VCC and minus VCC are plus 15 and minus 15, plus VCC is how much, plus 15, minus VCC how much, minus 15, right. The input to the non inverting terminal is 5 volts, this input is how much, this input is 5 volts, and the inverting terminal is grounded. You see inverting terminal is grounded. Find out value of the output voltage, that means that if the inverting terminal, this inverting terminal is grounded, that means V reference is connected to ground, that means here is 0 volts, right. So, now what we have, one input signal is 5, another input signal is 0. What is comparator? Comparator is, we have seen two things, right, V in greater than V ref, second was V in less than V ref. In this case 5 volts minus 0 volt. So, V in is greater than V ref or V is in less than V ref, which is the correct condition? You see V reference is 0, V in is 5. So, which is the condition, this first condition or second condition? Think, easy. So, the answer is first, right, because 5 volts is greater than 0 volt. So, the answer is this condition, and when you have this condition we already know then it is equals to plus VCC, right, this we know. When this is first condition, the answer is equals to plus VCC. But if it is second condition, which is V in is less than V ref, then our answer would be minus VCC. For this particular example, our answer is plus 15 volts, because it satisfies the condition which is V in is greater than V reference, and when we have this condition we know that V out is nothing but plus VCC, which is plus 15 volts. So, it is super easy. This is the easiest kind of circuit for you to understand when you talk about op amp, which is comparator, extremely simple and extremely useful, alright. So, this is about comparator. Let us see the next slide, and we have one more example. Let us see one more example. In this case, another circuit, again when you say another circuit, circuit is same. Here plus VCC, how much you are applying? Plus VCC and minus VCC are plus 15 and 0 volt. Okay. So, here VCC is given plus 15 volts, right, minus VCC is given 0 volts, correct. So, consider the op amp as comparator as shown below, okay, considered. Now, bias voltages are plus 15 and 0, done. Input to the inverting terminal is plus 5 volts. This input is plus 5 volts, alright. Let me write 5 correctly, 5 volts, alright, and the inverting terminal is 10 volts. This one is 10 volts. Find out value of output voltage, that is the question. Find out the value of output voltage when you are given these conditions plus 15, 0, plus 5, plus 10. In this case, let us again see what was the condition. V in greater than V ref plus VCC, V in less than V ref minus VCC, right. This is the condition. So, here what you see? You see this is V in, right, V in, this is V ref, V ref, V in is greater than V ref or V is less than V ref, then we can understand that the second condition is proper, which is V in is less than V ref, right, 5 volts is less than 10 volts. That is why we have to consider the second condition, and our answer should be minus VCC. So, here what we are given, minus VCC is 0 volt, minus VCC is 0 volt. That is why when you consider this particular example, right, in which your V in is less than V ref, your output will reach to 0 volts. So, your answer is V in is less than V ref, V out is minus VCC, which is equals to 0, right. So, you guys understood now what? First is VC comparator, right, we saw the function plus V in is greater than V ref is positive saturation, V in is less than V ref negative saturation, right. We have seen example, one example was plus 15 minus 15, and we have seen that V in is greater than V ref, then answer was plus 15. Second example plus 15 minus and 0 volts plus VCC minus VCC. In this case the given input voltages were plus 5 volts and plus 10 volts. Here we see that V in is less than V reference, and that is why the output voltage would be minus VCC, which is equals to 0 volts. Until now we have seen this much of things, right. So, it is extremely clear to all of us what exactly the comparator is. Okay, good. Now, if I really want to study the comparator, understand its characteristics or its application, I have to perform the experiment, right. Theory is okay, but we have to perform experiment, and if you want to perform the experiment, how can we perform this experiment, alright. So, you can see the circuit here is drawn, which is figure 2. What exactly the circuit is? Circuit is, if you see this one, alright, just concentrate on this part, which is I am drawing in a red kind of rectangle. You can see here there is one resistor R1, second resistor R2, value is 10k, value is 10k, right, and we are taking the voltage across resistor R2, across resistor R2. So, what is this? The circuit yesterday we have seen, or last module we have seen. What does this circuit is? The circuit is nothing but your voltage divider, right, voltage divider or potential divider, right. So, here your formula would be R 2 divided by R 1 plus R 2 into V in. Here what is V in? V in is plus 5 volts, V in is plus 5 volts. So, your R 2 divided by R 1 plus R 2, if all the values are same, R 1 equals to R 2, when you have case when R 1 equals to R 2, right. For this case your this formula, so let us write here, easy way of understanding, alright. So, we have this R 1, we have this R 2, right, R 1, R 2. In this case when R 1 equals to R 2, our formula was R 2 upon R 1 plus R 2 into V in, right. This will become, in this case R 1 equals to R 2, half V in, right. What is our V in? V in is 5 volts. So, if I replace V in by 5 volts, what will be my answer? My answer would be 2.5 volts. Answer will be 2.5 volts. That means that V reference here I am applying how much voltage? 2.5 volts. Alright. Now, we have a potentiometer, we have a pot. Yes, in the last modules we have seen what is a potentiometer and how we can change the resistance, right. Now, if I apply plus 5 volts across this pot, right, and if I generate a voltage here, then I can change the voltage depending on the change of the resistor. Here I am applying plus VCC, I am applying ground, and I have the output which is your LED, which is my LED. Here is the current limiting resistor to the LED. Now, what I have to see, if my V in, so lot of circles, let us remove it. If my V in, right, this is 2.5 volts, 2.5 volts. If my V in is greater than 2.5 volts, my output LED will glow, alright. And if my V in is less than 2.5 volts, then my LED will not glow, correct. So, what is written here? Let us see. So, let me just clear the screen. Alright, 2.5 volts. Connect the circuit as shown in figure 2. Okay, we will connect it. Apply V in through a potentiometer or variable power supply. Okay, through here we will apply V in. Observe V out and note down the value in table. So, we will apply V in, we have reference voltage, we will measure the V out, alright, and also observe how the LED is glowing as the potentiometer value is changed. So, we will see if we use LED it will glow, if we are not using it then we can only measure the V out, and this we will see that V out would be plus 5 volts. So, what we are assuming, right, if V in is greater than 2.5 volts, our V out will be close to plus 5 volts. If V in is less than 2.5 volts, our V out would be 0 volt. This is what we are assuming, alright. And let us do actual experiment and see whether we get these values or not, alright. So, let us again welcome Sitaram, who will help us to perform this particular experiment of a comparator, and we will see how this comparator can be, we can use op amp as a comparator and how this comparator circuit works, alright. So, you will see here on the breadboard, you see here on the breadboard what you can see a LED, right, and then what you see op amp, and then you have the current limiting resistor to the LED, and you are applying V reference through the potentiometer or through the potential divider, the two resistors, we are applying voltage 1 which is V reference to the one terminal which is inverting terminal of the operational amplifier, right. So, understand again, output is connected through limiting resistor to the LED, input inverting terminal connected through potential divider, right, to the op amp inverting input. Non inverting input will apply using the potentiometer or will apply using the power supply. So, let us here, so instead of this potentiometer converting the power supply, we can directly apply through this DC power supply, right. If you apply 0, 1, 2, 3, you will see at a point when it is greater than 2.5 volts, we will be able to see the glow in the LED, and we will measure the voltage across the potential divider initially, then we will increase the voltage and then we will see what is the output, alright. So, let us perform the experiment. We will apply bias voltage across the operational amplifier. So, you all know what is bias voltage, plus 15 minus 15, right. So, for this particular DC power supply, we already know the center terminal, 3 terminals in the center, right, red, black and green. Through that we can apply plus 15 and minus 15, alright. Now, you see so here, yes, in this case I am sorry, in this case since our circuit required plus 5 volts and 0 volts. So, that is why we are applying plus 5 and 0, not plus 15 and minus 15 for this particular circuit of comparator. Now, we have connected plus 5 volts to plus VCC, as you can see on the DC power supply, and ground to the minus VCC, alright. Now, we will apply voltage to the non inverting terminal of the op amp, alright. Now, let us first see what is the voltage across the potential divider. What is the voltage across the potential divider? Potential divider is this circuit, alright, it is this circuit. So, what let us see. So, we can use the multimeter, and we can see what is the voltage. So, if you see in the multimeters, you can see the voltage is about 2.5 volts, excellent. That means that the resistors that he has selected this time, they are extremely close or extremely accurate or having same value with minimum tolerance, right. That is why we see 2.5 to 2.501. So, that is good. So, 2.5 volts we are applying across the inverting terminal. Now, let us apply different voltages through the power supply to the non inverting terminal. So, can you please apply? Now, you see he is increasing from 0 slowly 1.7, 1.9, and we see there is no glow in LED, right. There is no glow, that means that your inverting terminal is still high, which is obvious because the inverting terminal is 2.5 volts, non inverting terminal is 1 volt. So, still V in is less than V ref. When V in will be greater than V ref, then only we can see the output plus 5 volts. So, plus 1.6, 1.2, 2.1, 2.2, 3, 4, 2.5, see 2.6, and suddenly at a certain point you should be able to see the LED working, or if the LED is not connected properly. Is it connected? Okay, because the second terminal of LED we have not grounded, that is why we cannot see, otherwise you will be able to see. Now, you can see here again, can you reduce the voltage please, so that students can understand. Reduce the voltage, you can see the DC power supply, he is reducing it to 2.4, bring it 2.4, yes. Now, you focus on this one which is your LED, and you cannot see LED glowing, right, you cannot see LED glowing. Now, make it 2.5. So, at 2.5 we can, now you see it is slightly greater than 2.5. As soon as it increases little bit greater than 2.5, you will immediately start looking at the LED glowing, that means that the output is high, very easy to understand, right. Now, if you keep on increasing it, does not matter because it cannot go more than 5 volts. So, 3.4, 3.5, 3.6, that is it, that is enough. So, you can just see that the LED is on, right, in this particular case when our V in is greater than V reference, and what happens when V in is less than V reference. So, let us slowly decrease the voltage and you focus here on the LED and you will see that at certain point if you compare keep on decreasing, keep on decreasing, keep on decreasing, keep on decreasing and it stops. First point stop 2.4, you see. Now 2.4, can you make it again 2.5, 2.4 to 2.3, 4 and 5, excellent. This 2.5, now we have measured through the V reference also, right, 2.5. So, this is not exactly 2.5, this is little bit 2.52 something, right. So, if you want to measure this voltage, you can see what is the input voltage 2. You can see here on the multimeter it is 2.525, it's 2.525, while your reference voltage, can you 2.524 volts is your input voltage. Now, you see the reference voltage across the potential divider, the reference voltage across the potential divider is 2.499 or 2.501. That means, your V in is greater than 2.5, which is reference voltage, that is why you can see the LED glowing. Very easy, extremely easy experiment, anyone and everyone can do it once you know what is comparator, right, alright. So, that is good that we have understood what exactly is a comparator. Now, all of us can perform this experiment of a comparator. You can go tomorrow and start doing a comparator and you can see by you can glow the LED. So, understand this thing, until and unless you ground the circuit it will not finish it, right, you cannot keep on hanging it. So, same thing when we are using LED with a current limiting resistor, you have to ground the LED, right. So, one is resistor, output, resistor, LED, ground, alright, and cathode is ground, not anode is ground, cathode is ground. So, LED works in a forward bias, you should know it. If you do not know it, I have to take a separate lecture, separate course for this to understand what is forward bias, reverse bias, how semiconductor devices can be operated, and if it is a photodiode how it will operate, if it is a LED how it operates, if it is a pin diode how it operates. But any case, anyway, I am assuming right now that you all know how to operate a LED, and when you have a LED then it can work in a forward bias condition. When this forward bias, that means your anode is positive, cathode is ground. In this case we have done the same thing and we could see how an op amp can be used as a comparator, and the LED was taken as an example to show that output is high and output is low, alright. So, let us move to the next module, and before we start the next module, what I feel is we have one more part of the comparator, and here it is very interesting, that is that if we draw the similar circuit which is here, right, what we have a similar circuit which is here, okay, and we want to test in a different way. What exactly we want to test? So, let us see, connect the circuit as shown in figure, okay, we will connect it. What is we have connected? Same thing, okay, plus 5 volts through the DC power supply will apply to V in, then we have potential divider 2.5 volts to V reference, okay, that is given. Now, okay, let us write clearly 2.5 volts, alright. Now, disconnect the potentiometer variable supply from V in, that means that we have to disconnect this one from the variable supply. Apply 5 volts peak to peak sine wave at 100 hertz directly to V in. Now, instead of applying here, what we will apply at V in? We apply 5 volts, right, peak to peak sine wave at 100 hertz frequency, at 100 hertz frequency, alright. So, observe the output V out and note down its peak to peak output voltage, comment on the shape of the output signal. So, we can use the oscilloscope and we can see the shape of the output signal. For first what we will do, first the same circuit we can use it, in just one thing we have to do different is that we have to disconnect this particular part, right, and connect this V in to the plus 5 volts peak to peak sine wave which is at 100 hertz, alright. So, let us do this experiment, let us see what kind of output voltage we observe, and then we also see what is the shape, because we have to comment on the shape, right. So, for commenting on the shape you have to first see what is the shape of the output signal. So, we will observe these two things. Let us see, once again let us call Sitaram to help us. All right. So, here we are applying 5 volts peak to peak 100 at 100 hertz. So, we are again using the function generator or signal generator. It generates signals at different frequency. So, what he is doing, he is now changing the frequency to 100 hertz and the voltage is already set at 5 volts, right. You can see, and he has pressed sine wave button for the sine wave. That means that we can apply sine wave of 5 volts peak to peak. You can see 0 millivolts to 5 volts, right. If you see on the screen, you can see it is from 0 y axis from 0 to 5 millivolts. That means peak to peak signal is 5 volts from 0 to 5 volts, frequency is 100 hertz and it is a sine wave. First what you have to do, you have to connect your probe. So, you have to connect your probe. Now, you have to check the probe with the oscilloscope. Yesterday also we have seen this, or in the last module we have seen this. Let us see once again. We have to connect the oscilloscope. Okay. Now, we have checked the probe. Now, we will connect the signal to see whether it is 5 volts and 100 hertz or not using the oscilloscope. Okay. So, we are connecting the probe, two probes together, and we are looking at the signal in the oscilloscope, and what we see is the voltage is 5.12 volts, right. Frequency is 99.8 100 hertz. Okay. So, now we make sure we now know that the frequency from the function generator is 100 hertz. We have also confirmed that the voltage from the function generator is 5 volt. We have also confirmed that the wave or input signal is sine wave. Three things we have confirmed. Now, we are connecting this sine wave signal at the non-inverting terminal of the operational amplifier. You see, so what happens when we apply 5 volts, you can again see the LED glowing. Can you see the LED glowing? Yes. Why? Shall I help you out? So, if you see, the LED is glowing because 5 volt is greater than your V reference voltage. 5 volts is greater than your V reference voltage. Now, we have to see the output voltage, right. So, before we see the output voltage, let us first again see the screen. Can you please see the screen? Yes. Here what we have done, see what he is doing, he is not connecting this, but he has connected here 5 volts peak to peak, right, peak to peak 100 hertz. This signal he has connected to the non-inverting terminal. This signal we have connected to the non-inverting terminal. Now, when he is applying 5 volts at non-inverting terminal, he could see that LED is on, because 5 volts is greater than 2.5 volts, right, 2.5 volts. What is 2.5 volts? V reference. So, input signal is greater than 2.5 volts, means output will be plus 5 volt, that is why LED is on, right. What we have to do here is that we have to observe the output voltage and note down its peak to peak output value. That means, how can we observe the peak to peak output value? We have to connect it to the oscilloscope. So, when I connect the output to the oscilloscope, and I will see what exactly the peak to peak voltage is there, alright. So, let us go back to the breadboard, let us see, coming back to the breadboard. alright. So, now he has connected the LED is still on, means the apply voltage is 5 volts, which is V in, reference voltage is 2.5 volts. Let us see the signal in the oscilloscope. Can you please see the signal in the oscilloscope? Can you show it? Alright. So, what we see, if you can zoom out, yes. So, you can you show Sitana where is our input signal? Input signal is this one, which is our sine wave, right. It is how much we have applied 2 volts, is it 2 volts input signal? Okay. So, 5.2 volts and 100 hertz, right. So, input signal was 5.2 volts, we all remember, because because it was 5.2 volts, that is why it is LED is on, otherwise LED will be off. But what is the output? What is the output? We can see output is 5 volts, right. We have 5 volts, is it 5 volts?
Approximately 5 volts.
Yeah, but it is close to 5 volts, it is close to 5 volts. But look at the shape, it is not any more sine wave, it is not any more sine wave. What it is? The square wave, it is the square wave. That means that even we apply sine wave, the output is what? 0 and 1. Indirectly we can say output is nothing but 0 and 1, that is a square wave, right. So, this is the beauty of the comparator, that your input signal is sine wave, your output can be square wave, alright. So, the point is that when we use a comparator, and we apply a voltage V in greater than V reference voltage, and the signal in at the input is sine wave, the output would be square wave. As you can see in the oscilloscope, that is input signal is sine wave and the output signal is square wave, right. Because the input signal is greater than reference voltage, that is why the output signal is saturated, and our which is equivalent to our bias voltage or close to our bias voltage. Our bias voltage is plus 5 volt and 0 volt, because V in is greater than V reference, that is why our output is plus V reference, which is 5 volts, alright. So, in this particular exercise, what we have seen, that we can use op amp as a comparator. Then we have seen that when we apply V in greater than and less than V reference, how can the comparator operate, and finally we have seen that when we use 5 volts sine wave peak to peak, right, then the output voltage here, the output voltage will result in a square wave, right. Applying a sine wave here, the output will be square wave, alright. So, I hope that you understood the role of an operational amplifier as a comparator, and you will go through this lecture once again, so that you completely understand what I have discussed in this particular module. And we will continue with the application of an operational amplifier as an integrator and as a differentiator in the following modules. How exactly the op amp can be used as an integrator and how we can use as a differentiator, we have to see in the following modules. So, for now we will stop this lecture at this point, and I will see you in the next module with the application of an operational amplifier as an integrator and application of an operational amplifier as a differentiator. Till then, you take care.